Hi, my name is Ekaterina. I'm from mechanical engineering, and I will be talking about the project that I've been working on in Tim Person's thermofluid lab, one of the projects. And yeah, it's called Multi-wavelength pulse LED system for high dynamic flow velocimetry. And I will start with actually what flow velocimetry is and why we actually care to visualize the flow. So basically, any system involving fluid, be it air or a wind or a car, water and pipe, blood and veins. Knowing how fluids move there is critical to improving designs, solving different engineering problems. And over the years, researchers have invented a lot of techniques to actually make invisible flows visible, like traditional methods like injected smoke or dye, up to more advanced digital techniques. And today I will be talking about one of the most widespread techniques at the moment, which is PIV, and how we want to improve it. So what is PIV? PIV stands for particle image velocimetry. It's basically a way to measure fluid velocity by seeding tiny particles into a flow, then illuminating them with high energy source, then taking a sequence of pictures with a certain time separation, and then using the software to actually track how these particles moved within the images. So it's became a gold standard now in labs and industry because it's giving quantitative data, and not only in a single point, but like across the entire field. However, traditional PIV systems have some drawbacks that still hinder their how and where they can be used. They still have a lot of limitations. And the major concern is cost. So all the systems rely on expensive, high-energy laser sources and high-speed imaging equipment that is quite costly, and we talk about tens to hundreds of thousands of euros just for a basic system. Next, there is safety. So all lasers used for PIV are typically class 4, which means they require safety protocols and some formal training. These systems are also quite bulky, and finally, they have so-called limited dynamic velocity range, which means they struggle to resolve both fast and slow motions at the same time. So how can we build a cheaper, safer, and more flexible system? So back in 2010, it has been shown that actually LEDs can be driven beyond their actually nominal voltage to produce the light intensity that is enough for PIV measurements. So we took this idea further, and we integrated not only one, but 3 LEDs, like red, green, and blue. And we flashed them in a single exposure of the camera, so we can get one image with 3 distant light sources. And this way, we actually get rid of the need of also high-speed recording equipment. So how this timing works, like imagine we have one exposure of the camera, and we have a seeding particle that follows the flow. So green LED flashes first, then after a short time we have a red flash, and then after a bit of a longer time we have a blue flash. So in the end we have an image where all 3 flashes capture a particle in a different time point in time. So, and then we can take this frame and separate 3 channels and actually get 2 or even 3 image pairs, and we can get 2 different velocity maps from just one single image. That's how we build it. So all 3 LEDs have their own driving circuits. They're driven by a microcontroller. And to achieve the desired microsecond accuracy, we had to program it on the assembler level way. Everything like cooling circuits is embedded into a single enclosure. Each LED has its own optical path with mirrors and filters, and we use fiber bundle and focusing the lens to actually shape that light into a single sheet that is needed for PIV measurements. To test our system, we used the classical case, which is submerged water jet heating on a flat plate. This case is great because it's relatively simple, yet it has regions, both fast regions, like high-speed core and was slow flow regions, like this wall jet and recirculating zones. So we seeded the flow with 10 micrometer glass sphere particles, and we validated the setup by using a standard technique called laser Doppler anemometry. So this is basically, I don't know if it's visible enough, but that's basically the raw images that we get in the experiments. We can see that particles are flashed in 3 different colors. We see like in the middle there, it's like faster moving flow, and then away from it, particles move slower, and actually these 3 colors almost overlap. To illustrate why traditional PIV systems actually suffer to resolve fast and slow moving flows, imagine we have like a really short time separation when it's fine for fast regions, but then slow regions just do not show enough movement so we can get the measurement. And on the flip side, if we choose the long time separation, then actually particles in the fast moving regions, they just move away from the interrogation window, and yet again, we just lose data. But if we use 3 colors, we can actually extract both long and short time separation from the same image. So here on the left, you see that like how short path separation actually works great for the fast moving regions, whereas long path separation actually gives some nonsense in the fast moving area, whereas it actually resolves these shear layers and slow velocity regions. And then we just need an algorithm, and we have this algorithm that actually decides that, yes, what kind of time separation we need in each point, and that will get us a more clear picture of the flow. So we validated it comparing against LDA measurements, and indeed, we can see here that compared to conventional PIV, which is just using 1 short time separation, our system is actually, our approach is actually does resolve better like slow velocity regions, and also what is important, turbulent fluctuations. Everything comes with a price. Of course, there is a trade-off. So first, that LEDs are not point sources. They scatter more than lasers, so it is really, really hard to collimate them in a way to get like a really thin light sheet needed for PIV measurements. Second, if we use 3 colors, it means we will have chromatic aberration. That's like that 3 colors will reflect differently, will focus differently on the lens, and we need to take care that it doesn't introduce extra bias error in the measurements. And lastly, that LEDs, they emit in the range of wavelengths. So sometimes the colors overlap, and that makes it much harder to actually separate them on the pre-processing stage. But yeah, these 2 problems are kind of being like solved in our system already. This problem kind of still persists. There is kind of a lot of improvement that can be done there. But anyway, to sum up, despite these challenges, the system is already built. It's cheaper, safer, and it's easier to use than traditional PIV system. It's completely laser-free. It gives enhanced velocity measurement, and yet it fits in the box, and it's very portable, so it can be used anywhere from the educational labs up to like big industry projects. And that is about everything that I